Today we're looking at the volume of a washer. So it's like this method, but it's when you rotate a shape around an axis that is not connected to your rotated shape. So if we look at, like, if I want to take this square here, okay, take this square, and I want to rotate it around the axis, I'm going to create the outer circle here, okay? And then the inner circle, that's a bad rotation. Let's try that again. Okay, outer circle, inner circle. Okay, so when I rotate it around, what we end up with is a washer. So think about your flag on a toothpick. I'm going to rotate it, but it's not connected at the end. I'm going to rotate it around and it's going to make like a donut. Yes, a donut. Okay, so we have two radii. Radii. So the first one is from the axis of rotation to the outer circle, and we call that big R. Okay. Then there's a second radius that we have to find, and it's the inner circle's radius, and we're going to call that one little r. Okay. So what we end up with to find the volume of our washer is basically the volume of the outer ring, so the outer circle, minus the volume of the inner circle, or little r. Okay. So same as we did for discs, we're just taking like the volume, we're taking out the donut hole. So the blue takes out the donut hole of your rotated object, okay? We can combine, because there's like a lot of factoring I can do here, we can combine our equations so that we just take one integral, so pi times the integral from a to b of the outer ring, oops, minus the inner ring. So the outer radius minus the inner radius. And this is generally the equation that I use to find my volume. Okay, so again, we use a disk if the region is rotating, that we rotate doesn't lie flat with the axis of rotation, because it creates a space or the donut hole in your rotation. Okay, so same thing, we're going to think about perpendicular, so same thing about disk, but it's doing disk method twice. Okay, so if I'm going to take a horizontal, if I have a horizontal axis of rotation, so like right here, I'm going to cut the shape, my area, perpendicular to the axis of rotation. So right now what I notice is that from the axis of rotation to the outer curve, we call that R. And from the axis of rotation to the inner curve, we call that little r. Okay, so again, the formula is listed here. For vertical axis of rotation, I'm going to say my axis is right here. So what we end up with is from the axis of rotation to the outer curve, that becomes our big R. And from the axis of rotation to our little curve, or to the inner curve, that becomes our little r. What we would end up doing here is swinging these curves around, so that these lengths around to create a washer. Okay, that's the best I can do. Here we go. Next. So we're going to find a bunch of volumes by using y is equal to the square root of x, y is equal to x squared, and then we're going to rotate them around different areas, okay? So I'm going to graph this. So y is equal to the square root of x, and y is equal to x squared is what we're using. So I know square root of x starts at 0, and then it goes up to 1, 1, and it's kind of arced like this. And then x squared is the same, but it's going to be arced concave up. Okay, so the area between these is what we're going to be rotating. And then what we want to do is rotate around the x-axis. So I am going to take around the x-axis here. I always like to draw where the rotation is. And so what's going to happen is since we are rotating the area between the two curves and the axis of rotation is horizontal, I am going to cut the shape vertically because it's perpendicular to your axis of rotation. So what will happen is that this outer point is going to swoop around like that, and the inner point will swoop around like that. So the outer R, there's a lot going on here, but the outer R is going to be from the axis of rotation to the outer curve. That's my big R. My little r is going to be from the axis of rotation to the inner curve. Okay, so we can like take some of this away. It just went backwards, sorry. Okay, so what we're gonna end up with is, wow. Okay, big R is outside, little r is inside. Big R, little r. So I write them here. R is equal to, the outer curve is the square root of x, and the inner curve is x squared. So the outer curve to the axis of rotation would be the square root of x minus 0, which is the square root of x. And then the inner curve is little r. So from the blue curve, which is x squared, and then it hits all the way back to the x-axis, which is 0. So little r can be defined by x squared. Now we find the volume. The volume is equal to pi times the integral from a to b of big R squared minus little r squared. And because we're working in terms of x, or remember we're stacking up the circles or stacking up the washers horizontally. Okay, so I get pi times, we are cutting the shape from x is equal to 0 to x is equal to 1. So our change in x happens between 0 to 1. Big R is the square root of x, and then we need to square that, minus little r, which is x squared, and then we need to square that. And then we want to take the integral of the whole thing. All right, so honestly, I did this in my calculator, and I got the volume is equal to 3/10 pi, or 0.3 pi. This is definitely one where you can take the integral on your own and it'll work out nicely, okay? All right, so the next one, we're gonna use the same curves. Y is equal to the square root of x, and y is equal to x squared. And we are going to rotate around the y-axis this time. So I'm gonna draw my axis of rotation, the y-axis. My curve goes from 0 to 1. That would be the curve, the square, y is equal to the square root of x. And then the bottom curve is y is equal to x squared. And then remember, since, well, okay, next up is to create a washer. So the I'm going to cut this shape right here. Okay, so to get the length of that, of the blue line, I'm going to have to take big R minus the inside part, which is little r. So big R is equal to the outer ring. So the outer ring would be dominated by this curve out here, which is the y is equal to x squared. But because we're working in, we are stacking up the washers vertically, then we're dealing with dy, so the change in y. Okay, so I need to solve for x. So x is equal to the square root of y, and for this curve, it would be x is equal to y squared. Okay, so r is equal to big R. Remember, that's from the outer curve to the axis of rotation. So the outer curve would be the square root of y and then minus 0 since you're stopping your length at y is equal to 0, x is equal to 0. Okay, so that simplifies just down to the square root of y. Little r is equal to the square root of x. Sorry, it was the square root of x, which is now just y squared minus 0. Okay, now we can set up our volume equation. So we're going to start with pi times the bounds of y from y is equal to 0 to y is equal to 1. Okay. From 0 to 1. So from 0 to 1 of r squared minus little r squared. So r squared is the square root of y squared minus little r, which is y squared, and then we have to square that dy, and then I just put brackets around the whole thing so that I make sure that I'm integrating everything between the integral and dy. Okay. And you might notice that this equation right here looks a lot like the one that we just did, because guess what? We're rotating the same area. So no matter if the washer is facing this way or facing vertically, then the volume is still going to be the same. Okay, so I'm going to end up with the volume is equal to 3 over 10 pi or 0.3 pi. All right, up next, same area to start with, but we're gonna rotate along the line, around the line y is equal to -1. So I'm starting with line of rotation at y is equal to -1. Okay, and I have a curve here that lasts between, that looks like that. Okay, so I am going to cut the shape vertically, and then I see that the outer ring has to do with the square root of x, and then the inner ring, little r, has to do with x squared. Okay, so we're going to start with big R. We take the outer curve, which is the square root of x, and subtract out, oh wait, these go all the way down to the line of rotation. So I need to subtract out -1, so I end up with a radius of the square root of x plus 1, which makes sense because we're actually adding a unit away from the x-axis, okay? And then the little r would be the x squared, and then that curve lasts until y is equal to -1. So x squared minus -1, which would be x squared plus 1. All right, we're ready to set up our volume. So if I were to rotate this, it would go like this, like the outer circle minus the inner circle. And then this is the volume, like one section of the volume we want to find. Okay, so the volume is equal to, and we are integrating in terms of dx. So from x is equal to 0 to x is equal to 1, so 0 to 1. I wrote those in weird spots, sorry. Of the big R minus little r, both of those values squared. Okay, so big R is the square root of x plus 1 squared minus little r is x squared plus 1 squared. And we're taking the whole antiderivative of that. Okay, so I get the volume is equal to, and again, type this into my calculator this time, and I got 0.966 truncated, or times pi, 0.967 times pi. Woohoo! Next up. Okay, same thing. but we're going with the line y is equal to 3. So 1, 2, 3, line of rotation. Okay, and I start with my curve. The outer curve is now the bottom curve. Notice they're going from this curve back to the line of rotation. So that's going to be my big R. And then the inner curve is the top curve this time, and that's my little r. So big R is equal to, it's always the top curve. To get the length of big R, we start with the top curve minus the bottom, okay? But when we're finding the volume of a washer, my big R is always the length of the outer curve, because it's not always the one on top. It's going to be the outer curve minus the inner curve, okay? So the outer curve would be, the length of the outer curve would be from 3, and then I'm going to subtract out the height of the outside curve, which would be x squared, okay? The inside curve, the length of the inside curve would be from 3 down to the square root of x. Now we're ready. The volume is equal to pi times the integral, and so what's happening is this inside ring is going to swoop around like that, okay? And the outside ring at the same x value would swoop around like that, and then one cross section of your shape would look washer. One cross section of your washer would look like kind of like that. Not that pretty. Okay, so how many times are we cutting up the figure? We're cutting it up infinitely between x is equal to 0 to x is equal to 1, or creating an infinite number of washers. So from 0 to 1. And of big R, which is 3 minus x squared, minus little r, 3 minus the square root of x, all squared, brackets. And we're cutting up dxy's, Hasselback potato, remember? All right. And then calculator, the volume is equal to 1.7 pi, and I believe I rounded that number because there was a lot of zeros in there. All right, let's do a couple more. Actually, let's do 4 more. All right, same curve. This time we're going to rotate around the line x is equal to 2, which is right here. It's vertical. And it looks like a flower petal kind of. Okay. So because we're going to rotate around a vertical line of rotation, I need to cut my shape up horizontally, okay, or with horizontal slashes. So this outer curve will curve around like this, create one circle, and then the inner curve will go like that to create one section of the washer. I'm erasing that. Okay, so the outside R, remember, is from the line of rotation to the outer curve, which is actually the square root curve. Okay. The inner curve is from the inner radius is from the line of rotation to the line y equals x squared. Okay, so big R is green. It's going to be, now to find the length of the radius, you always do the right curve minus the left curve when we're cutting horizontally, right? So we're at the x value of 2 minus, now remember you have to solve for x. So I get x is equal to y squared. So minus y squared, okay? And then little r, the blue, is we're starting again at 2 and going to the inner curve here, which is y is equal to x squared, or x is equal to the square root of y. So I'm going to subtract the square root of y. Okay, we can find the volume now. So the volume is equal to pi times, and we're integrating from x is equal to 0 to, sorry, y is equal to 0 to y is equal to 1. So 0 to 1 of the outside, just 2 minus y squared, minus 2 minus the square root of y, all squared, and then we take the integral of that, and we're working in dy. Again, when I put this in my calculator, I put all those y's in as x's just because the x button is so readily available, and you'll end up with the same volume, okay? So when I put this into my calculator, I get the volume is equal to 1.0333. No, that's too many threes. 1.033 times pi. Cool. Last one of this type, and then we'll move on to another. Okay. So I'm going to rotate the same shape, the flower petal-ish thing. Remember, this is y is equal to the square root of x, and the bottom is y is equal to x squared, which I'm going to rotate around the vertical line of rotation at -3. So I am going to have to solve for x again. So x is equal to y squared, and x is equal to the square root of y. If you were smart, you would have written these down at the beginning, and then you wouldn't have to solve for these every time you do one of these problems, but you know. All right, so the outer radius is from the line of rotation to the outside curve, okay? So that's big R. Big R is equal to the square root of y minus -3. So from the right to the left curve, okay? And then the inside curve is from the square, y is equal to the square root of x, or x is equal to y squared minus, so y squared minus -3. So I end up with y squared plus 3 as the radius for my inside, and the square root of y plus 3 for my outside. Time to find the volume. I get pi times the integral. How long are we cutting up the shape? Oh, you know, from 0 to 1. So from y is equal to 0 to y is equal to 1. The outside ring is the square root. I should be more better. All right. Is the square root of y plus 3 squared minus the inside ring, which is y squared plus 3 squared, dy. Calculator. Volume is equal to 2.3 pi. And again, there was a bunch of zeros, but it ended up rounding to 2.3. All right, last two. So we're going to find the volume of a solid form by revolving the region bounded by the graphs. Y is equal to x squared plus 1, y is equal to 0, x is equal to 0, and x is equal to 1. And we're going to revolve around the y-axis. All right, so I didn't draw this picture large enough on my paper, so I'll do more better today. All right, 1, 2. This is exactly what happened on my paper. Okay. All right, so y is equal to x squared plus 1 starts at y is equal to 1, and then I need to go up to 5. So over 1, up 1, over 2, up 1, 2, 3, 4. So I get my parabola like that. And then it says y is equal to 0, which is the x-axis. X is equal to 0. I got my curve. And x is equal to 1. Oh. Yeah, I overshot that a little. Okay, so here's the deal. I'm going to erase a bunch of this. And then make my life really easy. Okay. This is the y. The deal with this is that we're revolving around the y-axis, but part of the curve touches the axis of rotation and part of the curve doesn't. So the top part of the curve from y is equal to 1 and above, that is washer method, because there's a gap right here that creates the donut, okay? The part on the bottom right here, this is disk method. So I'm going to end up with 2 integrals to get the volume of the entire shape. But we can just add those together. Yeah. Okay, so disk is easy. Disk, we're going to go right curve minus left curve. So the radius of the disk is equal to 1 minus 0. The radius doesn't change. The radius is 1 the whole time, okay? The radius of the washer, though, that's another story, y'all. Okay, so I'm going to look at the washer here. It starts with this outer curve from 1 minus 0. That's big R. Okay, so big R is equal to 1 minus 0, which is 1. Now, little r is from the inside curve to, so the inside curve to the axis of rotation. So the inside curve is equal to y is equal to x squared plus 1. But since we're cutting dy way, we have to solve for x. So I have y minus 1 is equal to x squared. So x is equal to the square root of y minus 1. And it's positive because we're on the positive side of things. So the radius of the small inner ring would be the square root of y minus 1 minus 0, which is the square root of y minus 1. Okay, time to find the volume. The volume is equal to the volume of the washer plus the volume of the disk. Okay, so the washer is equal to pi times the integral. The washer is being cut up from y is equal to 1 to y is equal to 2. So 1 to 2. And I get the big R is 1 squared minus the inside, which is the square root of y minus 1 squared, okay, dy. And then we're going to add the disk. The disk is being integrated from at y is equal to 0 to y is equal to 1. 0 to 1. The radius is 1 dy. Okay, the volume of the washer is 1.5 pi. The volume of the disk is pi. No, it's 1. Sorry. 1 pi. Whoa. Okay. Which equals 2.5 pi. Woot. Okay, last one for real. The volume of the solid generated by revolving the region bounded by x squared, y is equal to 0, x is equal to 2, and the line x is equal to 3. So I'm going to start with the line x is equal to 3, just because that seems easier. And then I'm going to tackle this y is equal to 0 is the x-axis. X is equal to 2, be like right here. And then, and y is equal to x squared. X squared starts at 0, 0, goes up to 1, 1, and then 2, 4. So it looks like my region is the curve of the parabola, x equals 2, and y is equal to 0. Okay, so I'm going to revolve this region. My outer ring would be from the axis of rotation to the left curve, because this curve is going to swoop around like that. Whoa, okay. And my inside curve is the one at x is equal to 2, and it's going to swoop around like that to create. So basically the curve that's closer to the axis of rotation, that's going to be your little r. That's going to have to do with your little r. Okay, so erasing. Okay, so from the axis of rotation to your outer ring, outer curve, that's big R. And then from the axis of rotation to the inside curve, that's little r. So big R is equal to 3, right minus left, minus x squared. Little r is equal to, oh, wait a second. We're dealing with dy. We're cutting dy because we're stacking the washers vertically on top of each other. So y is equal to x squared. I need to isolate x, which gives me the square root of y. So instead of x squared, I need to write 3 minus the square root of y. Okay, little r starts at x is equal to 3 and then moves to x is equal to 2. So, and this is a constant distance. So the inside curve is a constant distance away from the axis of rotation. So it makes sense for the equation of the radius to just be 1. It's always 1 unit away. Okay. The volume is equal to pi times the integral. We are integrating from 0 to where the curve intersects with 2, which is 4. So 0 to 4. Of the outside curve, which is 3 minus the square root of y squared, minus the inside, which is 1 squared, dy. I used a handy dandy calculator and got 8 pi. All right, so a lot of this is visual. I like to draw it out. It definitely helps me. I draw the little circles on my paper, but it's really hard to see where the radiuses are when you do that. But honestly, it kind of helps me see what's happening with the shape. It might help you too. So yeah, that's it for today.